Alright, we're getting ready to get after another section here of trigonometry involving graphs. We should have a decent handle after the last section on the graphs for sine and cosine. So we're going to start off by looking at the reciprocals, which are the cosecant and secant functions, and then we'll look at the tangent and the cotangent functions as well. Now, if you remember that the cosecant of x is 1 over the sine of x, that means my variable's in the denominator, so I have to be careful of getting a 0 in the denominator because that expression would be undefined. And the sine of x does equal 0. You remember that the sine of x equals 0, at pi, at 2 pi, at 3 pi, and so on. In fact, the restriction on the domain of the sine, which is also, not of the sine, but of the cosecant function, is that x cannot equal any multiple of pi. It says pi k, where k is an element of the set of integers here, because you would get a 0 in the denominator. Now we know that when we are graphing rational functions, if you get a 0 in the denominator but not in the numerator, we typically have a vertical asymptote, and that's what's going to occur. We're going to have vertical asymptotes at x equal pi k, for k being any integer. Now, the period for cosecant is the same as the period of sine, and that is 2 pi. So as you can see here, I've made a table from 0 to 2 pi here, because what I want to do is I want to sketch, best that I can anyway, I want to sketch one full period of the cosecant graph here, and then I'm going to just repeat the process because it's going to be, it's a cyclic function, it's a periodic function, it's going to repeat itself. So I went ahead and I graphed, here in the pink, I graphed y equals the sine of x. And the reason I did that is that you can use that, the first time you're graphing this anyway, you can use this to help you come up with a sketch of the cosecant graph. So what I'm going to first do is I'm going to look to see that every time my sine crosses the x-axis, that means its y value, the y equals the sine of x, the y value would be 0, which means that the cosecant would be undefined. You see, I have just written down UNDEF, or undefined. So the first thing I'm going to do is I'm going to go ahead and I'm going to draw in some vertical asymptotes. Draw in vertical asymptotes here. And use a dotted line, don't use a solid line. I don't know how many of my students just think that they have to use a solid line every time there's an asymptote. And I'm doing this kind of freehanding it. As you can see, it's a little wobbly. And we have it. Here we go. Now, the values of x that I picked are from 0 to 2 pi, and so everything as far as my graph is going to be right in here. But as I mentioned, once I have this part of my graph, then I can continue it, the pattern, in both directions. So I'll use this kind of weird looking green one here, and I'm going to start graphing points. Now again, it's undefined here. At pi over 6, now remember this is pi over 2, so this is pi over 4, pi over 6 would be approximately here. At pi over 6, my y value is 2. So at pi over 6, I'm going to approximate this, my y value here is 2. At pi over 4, it's the square root of 2, which is about 1.4. Now pi over 4 would be about here. And then at pi over 3, which is to be about here on the x-axis, I'm at 2 square roots of 3 over 3. Now the square root of 3 is about 1.7. 2 times 1.7 is 3.4. Divided by 3 would be about 1.1, approximately. I'll write that underneath here. About 1.1. So, at about here, I'm way down here. And then, here's the cool part, at pi over 2, notice that the sine and the cosine here are both 1 because the reciprocal of 1 is 1. And so I'm right here at this point. And then I continue this. I have 2 pi over 3, and again about 1.1, so that'd be about here. And then at 3 pi over 4, this would be 1.4, about here. And then at 5 pi over 6, which would be about here, I'm at 2. And you get what looks a little bit like maybe the beginnings of a parabola. Now you've got to remember here, the closer I get to my values of 0 and pi, my graph, it's going to stay positive, but my y values are going to get bigger and bigger and bigger. And so what happens is we use this to help us guide the graph, and it's going to look a little like a parabola. It's not a parabola though. Oops. And so on. Now you put the little arrows on there, but you're going to have a lot of little arrows, so that'll keep you busy. And now I'll continue beyond pi. At 7 pi over 6, I'm at negative 2. Now 7 pi over 6 would be about here, negative 2 would be about here. Then at 5 pi over 4, which would be right here, I'm at negative square root 2, which would be about negative 1.4. And then at 4 pi over 3, which would be about here, I'm at negative 1.1 approximately. And then as you can see here at 3 pi over 2, I'm at negative 1. Notice the reciprocal of negative 1 is negative 1, and we hit that point again. So you can kind of see that the highs and the lows are kind of the lows and the highs of my graph, because this graph is going to curl right down. Watch it happen. 5 pi over 6. Wait a minute, that's not right. 5 pi over 6. I already had 5 pi over 6. This is 7 pi over 6. Excuse me, hang on. This is 7 pi over 6. Let's see. 5 pi over 3. Good Lord. Who made up this table? That would be me. Okay. Well, at least I found the mistake this time. And 5 pi over 3 here. So that's going to give me negative 1.1. Then negative 1.414. And then negative 2. And you can see that these values give me this kind of a looking inverted, kind of a parabola looking shape. But again, it's not a parabola, and we're going to use the asymptotes as a guide. Well, at least best I can here. And this graph continues. Now, this is not a continuous function because of the asymptotes and such, but within the asymptotes, your graph is continuous. There's no holes, there's no breaks. So I'm going to continue this, and I'm just going to approximate it here to kind of pick up the pace. Nobody likes a 20-minute video when it can be done in 15. And so on here. Let's see, it'd be about like this, I guess. Okay. And you can see how your graph looks. This is, remember, it's in the green here. Y equals the cosecant of x. Now, I graph sines and cosine functions all the time. I don't graph a lot of secants and cosecants, but that doesn't mean that you shouldn't have a good look at them, be able to graph transformations of these as well. But you have to know the basic parent graph for the cosecant, and that's the one here in this kind of bright green there. Now, let's skip over to the next one, which is the reciprocal of cosine. It's the secant, y equals the secant of x. Now, again, the variable's in the denominator, so there's certain values you must bypass. You cannot let the cosine of x be 0. And the cosine of x is 0 at like pi over 2, 3 pi over 2, 5 pi over 2. So I've gone ahead and listed the restrictions that x cannot equal pi over 2 plus pi k, k being an element of the integers, because those are the values that make this cosine 0, and you can't divide by 0. So you'll notice here at those values that for the secant, I have the values where it's undefined. Just like the guy over here, this guy is going to have some vertical asymptotes, and the vertical asymptotes are going to occur just like they did over here when your cosine graph, which I went ahead and did in purple here, is crossing the x-axis, because that's when the y value is 0, and that would give me a 0 in the denominator. So I'll go ahead, I've got a pink one here, hopefully it's got a little bit of ink, and I'll draw in, best that I can, my vertical asymptotes, and I'm going to go through kind of the same steps with the secant graph as I did with the cosecant. Because you should see this graph at least once in your trigonometric career. I can't remember if my trig teacher did it or not. For a small high school, I guess he was a pretty good teacher. He didn't teach me synthetic division. That would have been nice. Had to do long division for everything. So let's go ahead and let's find a good color here. Let's go with, we'll do the baby blue over here. Alright, so here's from 0 to 2 pi. Again, that's one full period because the period for secant of x is the same as the cosine of x. And I'll go ahead and I'll graph these. And I'll just start working my way through here. It's going to be in this part of the graph. And from this, I'll be able to continue the pattern to get the rest of the graph. So I have at 0, I'm at 1, which makes sense. See how it hits the high? And just like this one did over here, right? So then at pi over 6, remember this is 1.1. I'm at 1.1, so pi over 6 would be about here, 1.1, maybe about like that. Then at pi over 4, I'm at 1.4. The square root of 2 is approximately 1.4. And then at pi over 3, I'm at 2. And as you can see, just the same basic shape here, this is going to continue going this way. And I'm going to use this vertical asymptote as a guideline for my graph. Then I'm going to continue. At 2 pi over 3, I am at negative 2. I'm at negative 2. Let's see, that'd be down here. At 3 pi over 4, I'm at negative 1.4. So I'm approximating it best I can. At 5 pi over 6, I'm at negative 1.1. And then at pi, I am at, there it is, negative 1. Then it continues with this pattern. And I continue graphing best I can here. And you can see, again, it kind of looks like a parabola. It's not a parabola, it kind of looks like one. As far as your knowledge of graphs of algebraic functions, elementary functions. And I have this part. And this is going to continue. I've got a little bit more here because I've got to get to 2 pi. But at 5 pi over 6, I am at 2. I'm at 1.4. I'm at 1.1. And then I'm at 1. And you can see this part of the curve. Oops, I missed. That's why you always do it in pencil. Okay, now I'm just going to go ahead and complete the pattern and give you an idea of the rest of the graph. Kind of freehanding it here best I can. Trying to make it look nice and neat. Don't get too sloppy with this. You guys spend way too much time with your Desmos and your graphing calculators trying to copy off of that without actually plotting the points the first time you graph something. So the one here in blue, baby blue here, is y equals the secant of x. Now I want you to notice a couple things here. Did you notice here that for the one here in green for the cosecant, it's symmetric to the origin. This is an odd function. And over here, this is the one in baby blue here, this is symmetric to the y-axis. This is an even function. So let's write down some key ideas. For the cosecant of x, that's the first guy, the domain is all x except for those values, multiples of pi, integral multiples of pi, because that would give you a 0 in the denominator. And notice that the range, for the sine and for the cosine, it was between 1 and negative 1 inclusive. Well, when you take a number 1 and divide it by numbers between 1 and negative 1, you're going to get y values that are going to be greater than 1 or equal to 1, less than negative 1 or equal to negative 1. So you can see from 1 up and from negative 1 down. And this is the case. The domain, the range is the same for your secant here, although the domain is different because there are different values that give you 0 in the denominator, so you have to avoid those. Pi over 2 plus pi k, k being an element of the integers. Now, the period for both of these, as I mentioned before, was 360 degrees or 2 pi. Unlike sine and cosine, there's no amplitude because they're unbounded. They go up forever and ever, they go down forever and ever, so there's no amplitude. So you should try to remember some of this key information as we get through these graphs. Now we're also going to look in the next video at graphs of the tangent of x and the cotangent of x. They look quite a bit different than these guys.